Okay, let's go back to our lecture. I want to talk about this thing, the counterpositive. But first, I have to say something about the implication. Definition. A implies B is equivalent which has the same truth table is equivalent to non-A or B, not A or B. Okay, so let's see how we can describe it by truth tables. If I have A, B, I have not A, I have not A or B, which is what we shall call A implies B. True, true, false, false, true, false, true. False, what is not A, it is the contrary of A. So where A is true, not A is false. And where A is false, not A is true. Now we have or is commutative, so it's not important where I have one or the other. It will not be the same for implication, but not A or B is the same as B or not A, and it is what? It is true if and only if one of the two is true. Okay, at least one of the two. So not A false and B true, this is true. Not A false, B false, this is false. Both true, this is true. Not A true and B false is true. And so even if this leads to very counterintuitive ideas, A implies B is given by this truth table. A true, B true, implication A implies B true. A true, B false, be careful, implication A implies B false. A false, B true, implication true. A false, B false, implication true. This is something rather strange, but it is what we are building on when we do proofs of theorems, okay? And it is, as I said, very counterintuitive sometimes, also because we have an idea of implication as A causes is the cause of B. It's absolutely not like that. It is not a relation of cause and effect. The only meaning of A implies B in mathematics is given by this truth table, okay? I can try to help you with these A and B to see a bit the difference between implication and causality. A might be the light is on, and B might be there is current. Okay? And so, if we have that the light is on and there is current, this is something acceptable, okay? If we have that the light is off, you can very well have that there is current, but we have not turned on the light, okay? And so this is also a possible situation. It is possible that you have that the light is off and you have no current in the house. And so that's again a true implication. But you cannot have that the light is on with the absence of current. And so that is the false situation. But of course, you can see that this A implies B if and it is not so counterintuitive. If the light is on, you can deduce that there is current. This is the idea, okay? It's not, A implies B does not mean A is true, does not mean B is true. It means either not A or B or both. Either the light is on or there is current or both, okay? But you cannot have that the light is on if the current is missing, okay? But it is surely reversing the causality effect, because what causes the light being on is actually the presence of current. So you see that even this, which is not counterintuitive, the light is on implies that there is current, reverses the idea of effect and cause, okay? The light is the effect and the current is the cause, but A, the light on, implies B, there is current, okay? And this is the principal mechanism of all theorems. All theorems are in the form A implies B, which means not that A is true, not that B is true, but that A is true because of something else that you have proved, or something that you have checked directly, physically, then you can be sure of the truth of B as well, okay? Because when you have that the implication is true, this, and this, if you have that A is true, then you can be sure that B is true as well, okay? If F is false, you can have that B is true or false, but it's not what the theorem can tell you. The theorem can tell you that if A has been checked as true by any means, then you are sure that B is true as well, okay? Because this is not possible if the implication is true. Okay, so far for the definition of implication. Now, what happens is that, warning, A implies B is not equivalent to B implies A. Okay? Be very careful about this. I can use, I have been for many years, above all, a teacher at the first year of linear algebra. And so my preferred example of this is if two matrices are similar, and you remember what similar is, that A equals E inverse times A times E with the suitable matrix E, okay? Then if the two matrices are similar, then the two determinants are equal, okay? And so be careful not to reverse the implication. If two matrices have equal determinants, you are absolutely not sure that the two matrices are similar, okay? Because you might be in this situation, the determinants are equal, but the matrices are not similar, okay? What can you be sure of? You can be sure of that if the two determinants are not equal, then surely the two matrices are not similar, which is exactly this counterpositive or counter-nominal that we can trust very much. And so what we have is instead A implies B is equivalent to non B implies non A. Okay, and we can see it very easily. What is not B implies not A. By definition, this is equivalent to not B or not A, correct? And this is equivalent to not B is the same as B or not A. Yes, but in turn, this is equivalent because or is commutative to not A or B, which is equivalent to, because of the definition, A implies B. So they say exactly the same thing. So this is why we can trust these tricks in the sense G is isomorphic to H, then you have an isomorphism from G to H, then this isomorphism sends loops to loops. So if you have loops on one side, no loops on the other, you are sure that there is no isomorphism, and so on and so forth. So these are all one-way implications. And how can you use them? You find multiple edges on one side, you find multiple edges on the other side. Can you say these are isomorphic? No, you cannot say anything. But if you have multiple edges on one side, no multiple edges on the other side, you are pretty sure through the counterpositive that the two graphs are not isomorphic. You have a vertex of degree 5 in graph G. You have a vertex of degree 5 in graph H. You cannot say anything. But you have a vertex of degree 5 in G. You have no vertex of degree 5 in H. You are pretty sure that these two graphs are not isomorphic. Even also in this case, by using the counterpositive of an implication. The best possible situation in mathematics is when you have a double implication. A implies B and B implies A. Then you can totally substitute one thing with the other. It's extremely important, and when we will have some necessary and sufficient conditions, in the next few lectures, and I insist very much on how important they are. But if we have simple implications, A implies B, be very careful. One, not to reverse it. You go towards big mistakes. And two, look at what happens with the counter positive. A implies B. If you have A, you know something about B. But you cannot, by knowing that B is true, you don't know anything about the truth of A. But if you know that B is false, you are totally sure that A is false as well. The counter positive is very useful when you have a one-way implication. Okay? And so this is what we are using with these tricks. They are not tricks. They are uses of counter positive of direct one-way implications. Okay. I want to go to this. The K-cube is the graph whose vertices are the ordered K-tuples of zeros and ones. Two vertices being joined if and only if they differ in exactly one coordinate. Okay? Show that the, I don't mind these are very simple and okay. If you want, but it's very easy. I'm not interested in these two things, that the K-cube has 2 to the kth vertices and K times 2 to K minus 1 edges. The important thing is that I want you to prove that every K-cube is bipartite. And this is the first time we are, so to say, between two aspects of mathematics, okay? In general, you are a bit used to a very important thing, which is infinitesimal calculus, okay? Please remember that humankind, needed many centuries from the very sophisticated geometry of Greece to something absolutely new as infinitesimal calculus, okay? Many centuries. So it is important, it's the use of infinity which is something which was very heavy, very difficult, and also troublesome for scientists. Anyway, here we are using only finite things. But in this case, we use infinitely many finite things. Okay? Infinitely many. Why? Because we are talking about the K-cube for whatever K. So, let's see again what they say. The K-cube is the graph whose vertices are what? Ordered K-tuples of zeros and ones. And two vertices are joined, there exists an edge between two vertices, if and only if, as K-tuples, they differ by exactly one coordinate. Okay? So now, we can draw the one cube. One tuples of zeros and ones. So here we have just 0, here we have just 1. Do they differ by one coordinate? They have just one coordinate. Is it the same in the two vertices? No, they differ by just one coordinate, the only coordinate they have. And so they are connected. Is this graph bipartite? Sure thing. Oh, sorry. Okay? Next. 2 cube. So we have, you can think of starting from 2 copies of this. Sorry. And adding 1 extra coordinate before, in the sense that we can say that this is 0, 0, and this is 1, 0. So we had added a 0 at the end, and here we have 0, 1, and 1, 1. Okay? And so 2 copies, and actually, do these 2 differ by 1 coordinate? Yes, indeed. This coordinate. So we connect. Do these 2 differ by 1 coordinate? Yes, indeed. And so we have the 2 copies of what we had at the previous step. But also, now we have that similar objects in the same position, so to say, up and down, of course, differ only by this added coordinate. So this differs by the last coordinate from this. And so we connect. This differs by the last coordinate from this. And so we connect. Okay? We do not connect this to this because they differ by 2 coordinates. Neither these 2 because they differ by both coordinates. So these are the only ones. What about by partition? We already know the 3 cube. I need a new page. But look at here you have the previous page. And so what can we do? 2 copies, and I'll do that in a particular way, as was done in the book. And so this was 0, 0, 1, 0, 0, 1, and 1, 1. And now we add a 0 for saying the 0 copy. And now we do another copy. So 0, 0, 1, 0, 0, 1, and 1, 1, by adding the third coordinate, which is 1 for all. 1, 1, 1, 1. Do these 2, of course, we can repeat what we had in this page here, okay? And so surely we have this connection, difference by 1 coordinate, difference by 1 coordinate also here, difference by 1 coordinate, difference by 1 coordinate. Same thing here, just another copy of the 2 cube. Okay, here we are doing the 3 cube. Okay, but now, of course, we have 2 copies of the same things, only that we have an extra coordinate on the right, and of course, they are connected with the homologous one, so to say. So here, 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 and here. Okay? And our Turkish friend here in class has already discovered this. Oh, sorry. No. Okay, very good. But now the problem is take the 4 cube, the 5 cube, the 10 cube, the 100 cube, and prove that it is bipartite. How can you show that it is bipartite? Later on, we'll see a very nice theorem telling us how to recognize bipartite graphs. But for the moment, you have only one possibility, and it is to what we have done so far, to exhibit the bipartition, to say, in X I put these, in Y I put those. Okay? So this is what I invite you to do for next time. All right? But remember, it's not enough to say to show it for the 4 cube or for the 10 cube. You must do it for the K cube. So in absolute generality. Okay? They are finite. Each one of these is finite, is drawable, but there is an infinity of them because K can be any positive integer. Okay? So it is not difficult, but I suggest that you look very well at what we have here, at what we have here, at what we have here, and you discover a certain regularity, but this is your job, and I hope that that next Monday you come with a good idea. I don't want to know it now, okay? I want also our friends outside to have time. Stop. After, not now, not now. Okay. Good. I think these are enigmatic. This is rather funny. It can be funny, okay? But please remember, these are not so difficult. Still, no more than 15 minutes. Don't let them absorb you and devour you and eat your nights and so on. I know very well how they can eat one's night, okay? Also this, no more than 15 minutes for finding a non-trivial simple graph whose automorphism group is the identity, meaning that has as only possible isomorphism of it to itself, just the identity. Each vertex to itself, each edge to itself, okay? It's not so, I think this is a very nice example. Okay. We have time for incidence and adjacency matrices, okay? A nice way of representing a graph is by these two matrices. And for a while, it was the preferred way of storing a graph in a computer. Now there are more effective ways to do it, okay? But still, when thinking of a representation which is more combinatorial and not always drawing things in on a plane, okay, which is very nice, but it is limited in a sense, these matrices help quite a lot. And the adjacency matrix will be, anyway, a close relative to the adjacency matrix will be what is used by Google. And we'll talk about that much later. Okay, to any graph G, there corresponds a ni times epsilon matrix. Ni, remember, is the number of vertices. Epsilon is the number of edges of the graph, called the incidence matrix of G. Denote the vertices by V1, V2, V ni, and the edges by E1, E2, E epsilon. Then the incidence matrix of G is the matrix M of G with elements Mij, where Mij is the number of times, which can be 0, 1, or 2, that Vi and Ej are incident. Okay, my friends, when I ask you this notion, this is what I want you to say. I want you to express this definition in general, not just by an example. Then I will ask for an example. But I want you to be able to give a general definition. It is not difficult, but again, it is something for which I have not been able to approve many exams. I ask something and the student says, may I do it with an example? Answer, no. You must give me the definition. After which I ask you to give an example. But first of all, you are a graduate student, you are not a freshman, you must be able to give a general definition, in the sense that you must be able to program this for a computer. If you, for the moment, maybe in a while with deep learning and convolutional neural networks, it will be possible to give some 10,000 examples to the machine, and the machine will understand what the incidence matrix is. For the moment, it means 10,000 examples, not one. For the moment, if you want to program something, you must do it as in a mathematical definition. So I want you to be able to give a mathematical definition. Here we have one. The number of times 0, 1, or 2 that vertex vi and edge ej are incident. Okay? The incidence matrix of a graph is just a different way of specifying the graph. Another matrix is the adjacency matrix. This is a knee by knee matrix. A of G, given by elements A, I, J, in which A, I, J is the number of edges joining Vi and Vj. Is that so difficult to say? Why should I once more reject many students for not being able to give me such a definition? And now we can look at examples, of course, in which we see what? We see that the incidence matrix M of G has one column for each edge. And actually, what can you find in each column? Of course, you find what? Either 2 ones or 1 2. Okay? 2 ones when you have 2 different ends for that edge. And a 2 if you have that edge is a loop. Okay? And where are the 2 ones in this case? In correspondence of the rows, in the rows, corresponding to a vertex which is an end of this edge. And so here for E1, you find ones where in the first and second row, because first and second row correspond to these 2 vertices, which are the ends of E1. Why do we find 1, 0, 0, 1 in correspondence or in the column corresponding to E5? Because E5 has ends V1 and V4, and so we find 1 in column 1, in row 1 and row 4. Why do we find just the 2 for E6? Because E6 is a loop having both ends in vertex V4, and so we find the entry 2 in row 4. What about the adjacency matrix? Okay, this is since we have what we call non-oriented graphs, meaning that the edges are symmetric. There is no one way, okay, for the moment. And we have seen, we have a specific chapter concerning that, edges with a direction, which will be called arcs, okay? But this is not the case. So here the relation is symmetric and the adjacency matrix is symmetric. And so we find what? Let's read. Aij is the number of edges joining Vi and Vj. So, how many edges join V1 to V1? None, because there is no loop on V1, okay? How many edges do join V1 and V3? V1, V3, there is just edge E7, and so we find one, okay? V1, V3, 1. But if we take V1 and V2, we find two multiple edges, and so we have a 2 here, okay? And so on and so forth. Look, this is bigger and actually has more information than this, okay? All right, but also this matrix is very important, and something which is very close to the adjacency matrix is very important in the relationship between graph theory and analysis, because something very close to this will be called the Laplacian matrix and will be close to the Laplacian in analysis. And so I don't want to say bad things about adjacency matrix, even if it is, in principle, less information rich than the incidence matrix. Okay? So this, unfortunately, is no more true, as I was saying. This book is from a long time ago. It's from 1977, and at that time, there were no PCs, there were just mainframes, and so you must understand that something has changed from that time. Okay, let M be the incidence matrix and A the adjacency matrix of a graph G. Show that every column sum of M is 2. Okay? And this is not terribly difficult because we have that when we have loops, we have that the entry is 2 and not 1. Okay? This saves this little theorem. What are the column sums of A? This you should discover. It's not difficult. Okay? Forget about all these. Let me just give, I'll stop at 45. Let me just give some more terminology. A graph H is a subgraph of G. We shall write like this. If V of H is a subset of V of G, E of H is a subset of E of G, and psi H, the incidence function of H, is a restriction of the incidence function of G, okay? You can have also equality here. You might have that V of H equals V of G, and maybe E of H is really a proper subset of E of G. But, okay, of course, if you have equality here and equality here, you have that H is G, is equal to G. They are the same graph, okay? But when you have that H is a subgraph but is not equal to G, we say that it is a proper subgraph and we use this symbol instead of this, okay? If H is a subgraph of G, G is a supergraph of H. A very important particular situation is when we have a spanning subgraph or spanning supergraph of G, which is a subgraph or a supergraph with the same set of vertices, okay? So you can have a spanning subgraph which is proper even if the sets of vertices are the same. You have less edges in H than in G. It is important and it will be very important in the next chapter, okay, trees. And if we take a graph G, which has maybe loops and maybe multiple edges, and from G you delete all loops, and from every pair of adjacent vertices, you delete all but one link. Oh, sorry, I missed this. It was written before, but I didn't read it. Link is an edge which is not a loop. So edges may be loops if their ends are the same vertex, links if the ends are different vertices, okay? So if we delete all multiple edges but one surviving link joining them, we obtain a simple spanning subgraph of G, which we call the underlying simple graph of G. And here you can see a graph with all these edges, and thickened you can see the edges of a underlying simple graph. We have deleted this loop. Here we had two multiple edges, we have deleted one. Here we had three multiple edges, and we have deleted two and left one. Okay? And so this thickened one is A underlying, it's not its underlying, A, one of the possible underlying simple graphs of the given graph. Okay? All right, so here we have G, here we have a spanning subgraph of G because the set of vertices is the same. Here you have what is written here, that you have a non-empty subset V prime, the subgraph whose vertex set is V prime, whose edge set is the set of those edges that have both ends in V prime, is said to be induced by V prime. Okay, and that the G of V prime is an induced subgraph. You can also do the contrary, take away those vertices, and you have what is called G minus V prime. It is the subgraph obtained from G by deleting the vertices in V prime together with their incidence edges, and if V prime is just one vertex, we simply write G minus V. We see some of these examples here. Here you have vertex U and vertex V. If you delete vertex U and vertex V, you have also to delete all edges having at least one end in U or in V. And so if you delete U, you must also delete E and A. If you delete V, you must delete A, F, G, and B. And so you are left with this, which is G minus UV, okay? You can do the same thing with edges, of course, and you can, you have examples here, but I will come back to this very boring terminology at the beginning of next, not at the beginning, because the beginning will be devoted to the exercises, only one. The one of the K cube, okay, the only, okay, also the one of the graph which has only the identity as automorphisms. After that, we'll get bored with this terminology, and after that, we'll go on with, oh, here they are, vertex degrees with very interesting small theorems. Okay, with 2 minutes in advance, I greet you for your evening here in Italy, for your night in Pakistan and India, and also Iran. Libya is now more or less with us, and okay, I think a good afternoon in Mexico. Okay, ciao to everybody.
Thank you, Professor.
You're welcome.
Professor, when you will going to upload these slides?
Oh, tonight.
Tonight. And you are making...
No, sorry. Tonight I got some problems. Tomorrow.
Okay.
Professor?
Yeah?
Professor?
Yeah?
can we find this slide in virtual? Yes.
Okay, through virtual, you will be able to go to my homepage. In my homepage, in the page of the course program, you'll find the recording, the links to the recordings, and all these files. Okay?
Thank you very much, Professor.
You're welcome.